In this video, we will take a look at the concept of sum to infinity of geometric sequences. Suppose now we have a geometric sequence with the first term to be 1 and the common ratio to be 1/2. If we calculate the sum of the first 5 terms in the geometric sequence, that means S5, then we can apply the formula of the summation of geometric sequences. That means S5 is equal to 1 times 1 minus 0.5 to the power 5 over 1 minus 0.5. And therefore it is equal to 1.9375. Now let's try to add one more term to make it S6. And as we can see, we just need to change the power from 5 to 6. And therefore the answer is equal to 1.96875. We can actually observe that when we add more and more terms, the power will become larger and larger. When the power becomes larger, then the value of 0.5 to this power, that means the number in red, actually becomes smaller and smaller. On the other hand, we can see that the result of this summation, that means the number in orange, actually becomes closer and closer to 2. Such a result can be explained like this. If we consider the formula of Sn, that means the sum of the first n terms in this geometric sequence, then when n becomes very large, this arrow notation means when n approaches infinity, then we can see that the value of 0.5 to the power n will approach 0. And that means the value of Sn will be very close to 2 if n is very large, because 0.5 to the power n will then be very small, very close to 0. The result that we have just obtained here can actually be represented in this way. S infinity equals 2. S infinity means the value that Sn is approaching when n becomes larger and larger. Now let's try to generalize this finding. In general, if we can see that r to the power n approaches 0 when n approaches infinity, then by considering the formula of Sn, to calculate S infinity, we just need to substitute 0 to r to the power n. In other words, S infinity is just equal to a over 1 minus r. This formula of S infinity is only true when r to the power n approaches 0 when n approaches infinity. Now the next question is, when will r to the power n approaches 0? In order to answer this question, we can try to consider 5 cases of r. R can be less than -1, equal to -1, between -1 and 1, equal to 1, or greater than 1. In case 1, when r is less than -1, for example when r is equal to -1.2, then we can see that when n becomes very large, actually the value of r to the power n also becomes very large. R to the power n can be positive of a very large number or negative of a very large number. It depends on whether n is odd or even. In case 2, when r is equal to -1, then we can see that when n becomes very large, actually the value of r to the power n can only be positive or negative 1. And again, whether r to the power n is equal to positive 1 or negative 1 depends on whether the value of n is even or odd. Then in case 3, when r is between -1 and 1, for example when r is equal to -0.8, then we can see that when n approaches infinity, r to the power n will approach 0, no matter n is even or odd. For case 4, when r is equal to 1, we will not consider this case because Sn will be undefined when r is equal to 1. The reason is that in the formula of Sn, the denominator is 1 minus r. When r is 1, the denominator will be 0, which means it will result in an undefined value. For the last case, case 5, when r is greater than 1, for example when r is equal to 1.2, obviously we can see that when n becomes larger and larger, the value of r to the power n will also become larger and larger. Therefore, to conclude, only in case 3, the value of r to the power n will approach 0 when n approaches infinity. In other cases, r to the power n will not approach 0 and therefore S infinity does not exist. In other words, we can only calculate the sum to infinity, that means S infinity, only when R is between -1 and 1. Now let's take a look at a few examples and see how we can apply this concept of sum to infinity of geometric sequences. In the first example, we know that the first term of a geometric sequence is 2 and the sum to infinity is 8, and we are asked to find the common ratio of this sequence. In this question, we just need to apply the formula directly, that is a over 1 minus r is equal to 8. That means 2 over 1 minus r is equal to 8. After solving for r is equal to 3 over 4. And we can see that 3 over 4 is between -1 and 1. That means this result makes sense. Then we can draw the conclusion saying that the common ratio is 3 over 4. Next, in the second example, it is given that the first term of a geometric sequence is 3x squared, and the common ratio is x, and the sum to infinity is 4. Now we need to find the value of x. Again, we can apply the formula of S infinity to conclude that 3x squared over 1 minus x is equal to 4. After that, we will end up with a quadratic equation in x. Solving for x, we can get that x is equal to 2 over 3 or -2. Furthermore, since we know that x is the common ratio, then for S infinity to exist, the common ratio has to be between -1 and 1. And therefore -2 should be rejected, because -2 is not between -1 and 1. Lastly, in example 3, it is given that 2k, k, 1, so on and so forth is a geometric sequence, where k is a non-zero number, and then we need to find the sum to infinity of the geometric sequence. Firstly, we can calculate the common ratio immediately. It is equal to the second term over the first term, which means it is equal to k over 2k and it is equal to 1 over 2. Now we can see that this common ratio is between -1 and 1, and therefore it makes sense to calculate the sum to infinity. Now to calculate the sum to infinity, we need to know the first term. That means we need to know the value of k. When we consider that the ratio of the third term to the second term is equal to the common ratio, then we can conclude that 1 over k is equal to half. That means k is equal to 2. Now we can calculate the sum to infinity according to the formula. It is equal to the first term 2k over 1 minus the common ratio, which is 1 over 2. As a result, the sum to infinity of the geometric sequence is equal to 8. To conclude, in this video, we have learned how to calculate the sum to infinity of geometric sequences by considering a simple formula. However, when we apply this formula, we need to make sure that the value of the common ratio is between -1 and 1.